Hello everyone. Today, we're re-diving into one of the most profound, unbreakable limits of the entire cosmos, absolute 00 Kelvin, the coldest temperature that can ever exist in theory, and the single most impossible milestone to reach in the physical world. We all know what cold feels like. A winter breeze, a freezer's chill, the bite of liquid nitrogen on skin. But these are trivial, even warm, compared to the ultimate cold that haunts the edges of physics. For centuries, scientists have chased the dream of cooling matter to absolute zero, only to hit a wall written into the very fabric of space and time. This isn't just a technical challenge, it is a law of nature, one that shapes every star, every atom, and every corner of the universe we call home. To understand why 0 Kelvin is unreachable, we first must forget everything we think we know about temperature. Temperature is not just the measure of hot or cold. It is a direct count of how fast particles are moving. Every atom, every molecule, every tiny piece of matter in the universe is in constant motion, vibrating, spinning, colliding, dancing through space. When you heat a pot of water, you re-speeding up those water molecules. When you put ice in the freezer, you re-slowing them down. The colder something gets, the slower its particles move. This simple truth led 19th century physicists to a radical question. What if we could slow those particles all the way down? What if we could stop every atom completely with zero motion, zero vibration, zero energy? That point, they calculated, is absolute 00 Kelvin, or minus 273.15 degrees Celsius. It is the baseline, where all thermal motion ceases, the floor of all possible cold. But here, as the cosmic catch, we can never get there. The man who formalized this limit was William Thomson, better known as Lord Kelvin, the British physicist, who gave his name to the absolute temperature scale. In the 1840s and 1850s, Kelvin studied the behavior of gases at extreme low temperatures, and he realized that temperature couldn't drop infinitely. As gases cool, they shrink and their pressure falls. If you extrapolate this trend backward, you hit a temperature where volume and pressure would both reach zero, a point where matter itself can't get any colder. Kelvin called this the infinite cold of the universe, and he set its value at minus 273.15 degrees C, the number we still use today. But Kelvin didn't just name the limit. He hinted at its impossibility. He understood that cooling an object requires removing heat, and heat always flows from warm to cold. To reach absolute zero, you need a heat sink colder than absolute zero to pull the last bit of energy out of matter, and no such sink exists. This idea would later become the third law of thermodynamics, one of the four pillars that govern all energy and motion in the universe. The third law of thermodynamics states clearly it is impossible to cool a system to absolute zero in a finite number of steps. Let that sink in. Not hard, not impractical. With today's tech, impossible, full stop. Every time you cool an object closer to 0 Kelvin, it gets exponentially harder to remove the next unit of energy. Imagine trying to empty a bathtub that keeps refilling with a tiny drop of water every time you scoop some out. The closer you get to empty, the slower you go, and you'll never get every last drop. That is exactly what happens with absolute zero. The closer we get to 0 Kelvin, the more energy we need to cool it further until the effort required becomes infinite. But the third law isn't the only reason absolute zero is out of reach. The real killer comes from quantum physics, the weird counterintuitive rules that govern the smallest particles in the universe. In the early 1900s, quantum mechanics upended everything we thought about motion and energy. Scientists discovered that particles don't behave like tiny billiard balls. They act like waves, and they rebound by the Heisenberg uncertainty principle. This principle says we can never know both a particle's exact position and its exact momentum at the same time. If a particle were truly at absolute zero, it would stop moving entirely. We know its position perfectly, and its momentum would be zero. That violates the uncertainty principle on a fundamental level. Quantum physics demands that, even at the coldest possible state, particles can't be completely still. They retain a tiny, irreducible amount of energy, called zero-point energy. This isn't leftover heat. It is built into the particle itself, a minimum amount of motion that can never be removed. It is the universe way of saying nothing can ever truly stop. Even in empty space, vacuum energy and quantum fluctuations keep particles fizzing with activity, a constant hum that prevents absolute stillness. To see how hard we've tried to reach absolute zero, let's look at humanity's long journey into the cold. For most of history, humans had no way to create extreme low temperatures. The coldest thing we could make was ice mixed with salt, which only drops to about -21 degrees C. Everything changed in the 19th century when scientists began liquefying gases. First oxygen, then nitrogen, then hydrogen. Each one unlocked colder temperatures. Hydrogen liquefies at -253 degrees C, just 20 degrees above absolute zero. Then, in 1908, Heike-Kamerlingh-Onnes liquefied helium, reaching -269 degrees C, a mere 4.2 Kelvin. This was a revolution. Onnes won a Nobel Prize, and he discovered superconductivity along the way. Materials that conduct electricity with zero resistance at ultra-cold temperatures. But even liquid helium was still 4 degrees above absolute zero, a gulf that seemed uncrossable. The next leap came in the late 20th century with laser cooling, a technique that won its inventors a Nobel Prize in 1997. Lasers slow down atoms by hitting them with photons, sapping their momentum bit by bit. Using this method, scientists cooled atoms to less than a billionth of a Kelvin, so close to absolute zero, you could barely measure the difference. We created a state of matter called Bose-Einstein condensate, where thousands of atoms act as a single quantum particle, a bizarre form of matter that only exists at nanokelvin temperatures. It is the coldest matter we've ever made, a triumph of human ingenuity, but it is still not 0 Kelvin. That tiny fraction of a degree above zero is a gap we can never close, thanks to zero-point energy and the third law. What about the coldest places in nature? Surely, the empty vacuum of space is close to absolute zero, right? The cosmic microwave background, the leftover heat from the Big Bang, fills the entire universe at a temperature of 2.7 Kelvin, still nearly 3 degrees above absolute zero. There's a nebula called the Boomerang Nebula, about 5,000 light-years from Earth, which is the coldest natural place we've ever found. Its temperature is just 1 Kelvin, half the temperature of deep space, colder than any planet, any moon, any dead star. But even the Boomerang Nebula is 1 full degree above 0 Kelvin. No natural object in the universe, no matter how remote or how empty, ever reaches absolute zero. The universe itself is too energetic, too quantum, too alive to let that happen. Let's think about what reaching absolute zero would actually mean if it were possible. If all particle motion stopped, matter would lose all its properties. Atoms would collapse in on themselves. Electrons would fall into atomic nuclei. Chemistry would cease to exist. Stars couldn't form, planets couldn't hold together, life couldn't exist. Absolute zero isn't just a temperature, it is the death of the universe as we know it. The fact that it is unreachable is what allows the cosmos to function. It is a safeguard built into physics, keeping matter stable, energy flowing, and the universe dynamic. Every time we get closer to 0 Kelvin, we learn more about the universe's basic rules. Superconductivity, quantum computing, ultra-precise sensors, all these technologies come from studying matter near absolute zero. We don't need to reach the limit to benefit from chasing it. The quest for absolute cold has pushed physics forward for 200 years, revealing secrets of quantum mechanics and thermodynamics that we never would have found otherwise. Absolute zero is a ghost, a theoretical ideal that guides our science, but remains forever beyond our grasp. It is a reminder that the universe has limits, and those limits are what make it beautiful and functional. We can explore the coldest corners of space, build machines that cool atoms to near nothingness, and write equations that describe 0 Kelvin perfectly, but we can never touch it. It is the ultimate cosmic mystery, a line in the sand that separates what we can do from what the universe allows. In a universe full of black holes, exploding stars, and infinite galaxies, the simplest, most fundamental limit is a temperature that doesn't even exist. It is a humbling thought. We can send probes to Pluto, photograph distant nebulas, and split the atom, but we can never make something perfectly cold. Absolute zero is the universe's way of telling us that some things are meant to stay out of reach, and that's okay. The magic isn't in reaching the limit, it is in understanding why it is there, and in marveling at the rules that make our universe work. Every cold day, every frozen lake, every sip of iced coffee is a tiny reminder of this cosmic truth. Temperature is motion, motion is energy, and energy can never be fully erased. The universe is always moving, always humming, always alive. And that's why 0 Kelvin will stay forever impossible. Please like, comment, share, and subscribe to the channel.